So here's a picture from your book that shows a much prettier version of the electric and magnetic fields for a wave that is traveling to the right on this screen. So that's the direction of travel. That's your V, going at the speed of light. All electromagnetic waves go at this speed, which is given by C, which is 3 approximately times 10 to the 8 meters per second. And we can describe waves in terms of their frequency and their wavelength. And wavelength we write as lambda, and frequency we write as a script F, or sometimes we write it as the Greek letter nu. So frequency is measured in 1/seconds or hertz, and wavelength is going to be measured in a length, obviously, meters. And so here the wavelength is the distance between the crests or the troughs, and the frequency is how fast it oscillates up and down. So the frequency of our light is determined by the oscillating charge. So if we think back to this simulation, the frequency of the oscillation depends on how fast this is moving up and down. This is higher frequency, and this is lower frequency as we go along. Depending on the frequency determines what kind of light we're looking at. So this is a chart of the electromagnetic radiation. There's a lot of information here. It's showing you both wavelength sizes. So this is looking at this chart, this is the radiation type, the wavelength. And so the scale tells you sort of the size. So radio waves tend to be about 10 to the third, or about 1,000 meters in length. Microwave are on the order of centimeters, and so forth. Visible is really quite small, 0.5 times 10 to the minus 6. And then we've got ultraviolet, X-ray, and gamma. And the smaller the waves are, the closer they are in size to atomic things, is when they can do some damage to your atoms. So that's why we worry about ultraviolet radiation, because it's on the order of the size of molecules. X-rays as well, and then gamma rays are particularly bad for us. And this is what comes out of sometimes nuclear reactions, is some gamma rays. This tells you your frequency, and if you take obviously the wavelength and you multiply it times the frequency, so wavelength times the frequency, you'll always get the same number. So as your wavelength for large wavelengths, you're going to have a small frequency, and for small wavelengths, you're going to have a large frequency, so everything can match the speed of light. And then it turns out that the color of the light, if you like, or the frequency is really color in terms of the way physicists approach it, that there's a characteristic frequency and wavelength associated with different temperatures. So a colder object radiates radio waves, warmer is infrared, and even warmer is visible. And you know this as you see different flames. You know that flames that are red are not as hot as, say, blue flames. We have a very small window we can see, obviously. We see not much at all. We're just right in this sort of range here, depending on the scale. So we have a very small window that we can see, but we can detect across all of these wavelengths as we go along. So the frequency gets determined. Frequency is determined by the oscillation of the charge. Frequency by oscillation. And C is set. All light travels at this speed. And then our wavelength is just what we measure as a result. And our wavelength can change. So lambda can change as we go through different materials, because as we send radiation through different materials, it effectively slows down, which means this wavelength changes, and that's what describes the bending of light. So we're not going to do much in terms of calculations with this. I just wanted you to have this background. What we're going to do is look at light interacting. So we want to look at light, particularly visible light, interacting with surfaces. So interacting with mirrors, so reflection, and then glass, where light is going to refract and bend, as well as looking then at lenses. So we're going to look at applications. So we're going to look at applications of using electromagnetic radiation, but we won't try to describe them in terms of the equations we've developed. We'll do them in a more geometric fashion. So we get to leave our integrals for a little while and just do some geometry along the way.